Okay, Assalamualaikum. My name is Dr. Adam. I will cover lecture 4 and 5, advanced database searching and multiple sequence alignments. Last week, I have uploaded video into Ultra BLAST for you to follow the lecture for advanced database searching. Today, I would like to have a tutorial so that you can understand the topic better. I think this might be a better way for you to learn bioinformatics rather than go through the lecture one by one. Okay. Do you have any difficulty to follow the lecture for advanced database searching? Have you watched the video before? Hello?
Yes, Doctor.
Yes,
Yes.
Doctor.
Okay, before I go into advanced database searching topic, this one to recap back for the previous chapter that you have learned before. What are the limitations of standard BLAST? Who can answer this question? I prepared this tutorial in the format that is very, it sounds something like what I'm going to ask during the exams. Okay, what are the limitations for standard BLAST? The standard BLAST can be BLAST P, BLAST N, right? So if you perform BLAST P against a protein database, what is the limitation of standard BLAST? Do you know what is BLAST P? Yeah. For standard BLAST P is mainly for finding sequences with high identity, normally more than 30% identity. If the sum of the homologous proteins is less than 30% identity, could be between 25 to 30% identity. In that case, the BLAST P may not be efficient, may not be good enough to detect distant homolog. Right? So these are the limitations for BLAST P. When you use human beta globin as a query against human red set proteins, and BLAST P does not find human myoglobin. Okay, this is because the human myoglobin is distantly related to hemoglobin. Hemoglobin is in the form of tetramer, 4 subunit, and then myoglobin is in the form of only 1 subunit. And then the subunit for myoglobin is highly similar to the subunit of hemoglobins. In fact, they are homologous. Just the standard BLAST P is not effective enough to detect distant homolog. Even though you can detect with BLAST P, the E-value that reported to you may not be significant. Right? So when you like to perform or to search a long length of the genomic DNA for more than 10,000 base pair, could be 10,000, 100,000 base pair of DNA fragments to BLAST against or to align with the genomic DNA in the sequence, in the database, the BLAST N is not effective for you to do the search for for genomic DNA more than 10,000 kilobase pair, because it's too time efficient, too time consuming. Do you know that? What the seed numbers are for the BLAST N? The word size for BLAST N is
24.
When you perform BLAST N, have you checked on the parameters inside? What is the word size for BLAST N? 1, 2, or 3, or 5, or 10, 20, 28, 11.
3.
No, BLAST N is not 3. 3 is BLAST P. BLAST B, the word size is 3. For BLAST N is 11. Because of 11, and then the BLAST N is not effective, it's not good enough to search the long length of the DNA sequences. And this is one of the limitations for standard BLAST. Okay? So in order to overcome this limitation, and then you have to use specialized BLAST. For example, Psi BLAST, Phi BLAST, Mega BLAST. These are examples of the specialized BLAST for you to search low identity homologous protein, for you to search long length of the DNA sequences against database. Okay. Okay, can you answer this question? BLAST P search using retinol binding protein as a query only reported hits from retinol binding protein. Okay, when you use one of the members from retinol binding proteins to perform BLAST P search against protein database, and then you only the BLAST P only report to you the members from retinol binding protein. They will not report to you the members from apolipoprotein or orthorhombic binding proteins, because these two are too distantly related to retinol binding proteins. How do you refine the BLAST P search in order to detect slightly distantly related proteins? So if you like to detect, you have to widen the scope of the detection, maybe to some of the members of apolipoprotein. What can you do? How can you adjust for the parameters for the BLAST P search in order for you to detect slightly distantly related proteins?
Use higher pen
BLAST.
or lower blossom.
Lower blossom.
Lower blossom.
Lower blossom and higher?
Higher pen.
Okay, good. Okay. But they are limitation. Even though you use a lower blossom and higher pen, it still can allow you to detect a slightly distantly related protein. Maybe up to here, right? Right? Only widen the scope a bit, but it cannot widen the scope further to the entire apolipoprotein or orthorhombic binding proteins. Halo, dengar tak? Halo.
Dengar.
Dengar, Doktor.
Malah saya ada live online learning. Okay. Okay. You can perform. You can widen the scope of the search using the BLAST P by adjusting the scoring matrix, right? To blossom 45 and pump 250 in order to detect slightly distantly related proteins. And in some cases, when the identity between your target protein and also the protein in database is between 25 to 30% identity, the inference of the homology may not be clear. Yeah, because sometimes the E value that reported to you maybe is higher than expected E value of 0.05 for significant homology detections. So in that case, you have to perform additional step in order to check whether the output that reported to you is homology to your protein or not. And then one of thing you can do is performing reverse blast, like you learned before, like in chapter 4, reverse blast. You can use the output protein as query against protein database, and then check whether it will report to you your origin protein, retinal binding protein or not. If yes, meaning that these two proteins are homologous, right? Okay. If you perform blast pieces for retinal binding proteins reported unclear homology with non-significant e-value of 0.27 using default parameter setting. And then how do you detect distantly related proteins? How do by using BLAST-P, you are only able to detect slightly distantly related proteins with unclear homology. How are you going to solve this in order to detect distantly related protein with clear homology? Okay, one of the application you can use is using BLAST. One of the software under advanced database searching, BLAST. Right? Okay. Okay. If we stick to the rule of e-value less than 0.05 as homology, BLAST-P fail to detect homologous proteins. Complement component protein with e-value of 0.2 e-value with e-value of 0.27 just now with e-value of 0.27, right, which is not significant, right? And bit score is 33.9. If the search and then it will report to you one of the protein which is component complement A proteins with e-value of 0.27 and big score of 33.9. But if you use BLAST to do the search, the BLAST reported significant e-value for CC8 protein and classify it as homologous protein after iteration 3. Right? This is because the BLAST, they customize a specific scoring matrix called position specific scoring matrix or PSSM based on input multiple sequence alignment information from the previous iterations. So meaning that you obtain a result that report to you CC8 is homologous to your input proteins, meaning that based on the multiple sequence alignments from iteration 2 to perform PSSM, then you're able to detect a homologous CC8 protein at iteration 3. The multiple sequence alignments provides information about unique profile of accepted mutation in the query and its nearest database match. Right? In BLAST, the e-value was dramatically lower as a result of using scoring matrix, which is very specialized, specially constructed for this family of proteins. And then BLAST categorized CCA protein as homologous, not like BLAST-P search. They use the same scoring matrix, for example, Boson 62 for all of the proteins that you search in database. For BLAST, it's different. For every single iteration BLAST, it customizes a specific PSSM to do the search. That's why the BLAST is very specific and very sensitive because the input sequence is from the homologous sequences that you obtain from the previous iterations. Okay, these two are the scoring metrics for Blossom 62 and also from side blast. We call it BSM. For blast B, the same scoring matrix will apply to all. You see, when alanine and then score assigned is 4, regardless what protein that you use, it will still give you score because the blast use the same scoring matrix for all of the blasts. But for side blast, it's different. Side blast use a called BSSM with different score at various positions. For example, alanine at at position 6, 14, 15, 16, 42. You see different score to alanine residues at different position of the sequence. Okay? Same as at position 13 and also 40. Different score to tryptophan at various positions of the sequence alignments. Right? Okay, this is because the PSSM is derived from is derived based on side blast output, which reported significant E value. For example, the output that you detected at iteration 3 is depending on the output that you obtain in I2. Those information will be used to construct multiple elements, and the information from the multiple elements is then converted into the form of PSSM. This PSSM will be used as input for you to do the search for iteration 3, same as iteration 3 and 4 and 5, and then a customized PSSM will be used as subsequent iterations. Okay, how to construct PS? Okay, when you perform side blast first and CBI database, everything that you want, you don't know how the PS is constructed. Now I give you not be nucleotide sequence because the side blast is for protein blast. It should be amino acid sequence. Somehow, this example is more simple to follow. That's why I use a nucleotide sequence to construct the PSSM so that you can follow how PSSM is constructed easily. Okay. The value in upper panel are calculated based on the frequency of occurrence of particular nucleotide at selected column. Right? For example, at column 1, they are 1, 2, 3A, 1C, and 1T. So the frequency for A to align at the column 1 is 3 over 5. 5 is total members here. 3 over 5 equal to 0.6. So you get at column 1, A is 0.6. So the frequency for A is 3 over 5 equal to 0.6. And then overall frequency for A is the average. This overall frequency for A is the average. Is the average of the frequency for all the A in each column. So meaning that you add 0.6 plus 0.6 plus 0.4 plus 0.2 divided by 6, and then you get 0.3. Right? So this is overall frequency. You can calculate the rest. And then the lower panel, this panel representing normalized frequency of occurrence. Okay, they will normalize the value inside here. For example, at column 1, how to calculate this normalized frequency is very easy. At column 1, for A is just now A is 0.6, and then the overall frequency is 0.3. So 0.6 divided by 0.3, you get 2 here. Right? So can you get me the X and Y value here? What is the X value here? And Y? Can someone answer this question so that I know you understand this? Can you provide me the answer?
X is 0.4.
X is 0.4. And then Y?
1.74.
1.74. Okay, you divide this. Okay, good. Okay, and then this the answer. Okay, I highlight this. X is 1.74 and 0.4, yes. Okay, and then in order to reduce computational time needed to do the calculations, the score of BSSM are normally converted to log format. Right, this score will be normally the score here will be normally converted to the log format. This is in the log format. Why? Do you know why? Because in order to reduce computational time, when the software they use, they do the calculation, if you convert it into the log format, easy for them to do the calculations. If you reduce the time to do the calculation, so that you no need to multiply the individual match score here for the final score. For example, if the BSSM is not in log format, you have to multiply every single match in order to get the final score. But for PSSM, normally if you convert into the log format, log or launch format, and then you don't need to multiply the score in order to get the final score. You just have to add on every single match here in order to get the final score. Okay? So if you use the BSSM to search again database with sequence S1 and S2, which of the sequences in the database best match to the BSSM here? Okay, this one you can think of the answer, and then let's say if one of the sequence in the database is AACTCG, since the BSSM is in the form of log format, and then you no need to multiply every single match value in order to get the final score. You just have to add on every single match value. For example, AACTCG, A is 1, A is 1, and then C is 0.8, and then T is 1, and then C is 1.38, and G is 1.15. So you just add on every single match score in order to get the final score. The final score is 6.53, right? Very simple, right? To calculate. And then because of the format of BSSM is in the form of the log format, so it simplifies the calculation later on. Right? So, okay. So for these two sequences in database, for example, if you use this to score the sequences in the database, and then you have two sequences in the database, S1 and S2, which one do you think that is match better to your BSSM here? Which one do you think is more matched? Do you know how to calculate score? AAC, TCT. So A 1 plus 1, and then C plus 0.8, and then T plus 1, and then C plus 1.38, and then T plus 0, and then you get the score. And then for TTG, AC, ATG, so T 0, T 0, and then G is 1.15, and then A is 0.41, and then followed by T is 0, and then G is 1.5, and then you get another score. So when you compare the score of 10, you get this. for the sequence 1, the total score is 5.18. And then for sequence 2, the total score is 2.71. So what you can conclude here is the sequence 1 match better the BSSM here. Right? That's why you obtain this S1 sequence will then report to you as a batch match sequence in the database using the BSSM that you have constructed from previous iterations. Do you know how to construct BSSM? So if example, okay, after you perform side blast at iteration 1, and then you obtain a list of the sequences with significant e-value. And then these sequences will be aligned in the form of multiple sequence alignment. You will perform multiple sequence alignment to align these sequences. And then from the multiple sequence alignments, the information is the alignment of the MSA will be converted into BSSM. And then this BSSM will be used as an input to search against database, no longer the input sequences that you use to do the search in iteration 1. Do you understand? Faham tak?
Yes.
Okay, it's very simple.
Doktor boleh terangkan balik ke doktor? Confused.
Which one? Which one?
The part where actually PSSM tu is being calculated so that dia boleh incorporate with the data sequence yang doktor cakap tadi.
You mean the calculation on this slide or not in the slide?
The one yang doktor cakap not in the slide.
Oh, not in the slide. Okay. Okay. So you perform iteration 1, and then you get sequences with significant hit, meaning that with the good e-value, okay? So you get sequence 1, then sequence 2, sequence 3, and then with not significant hit, you obtain sequence S4, S5. Okay, this is the output they obtained from this is the output they obtained from iteration 1. And then since only 3 sequences reported with good e-value, the default e-value for side blast is 0.005, right? So if this, meaning that if they reported these 3 sequences to you, meaning that the e-value here is less than 0.005, right? So, and then these 3 sequences will be used to construct MSA. So this 3, okay, 3, okay, and then you perform MSA for sequence 1, 2, 3, right? And then converted to BSSM. So now you would like to perform second iterations. For the second iterations, this one will be used as input. Right? So once you get the hit and then you perform multiple sequence alignment, and then the input for multiple sequence alignment will be converted into BSSN. Same thing as what I teach you just now, right? You get the BSSN, and And then this BSSM will be used as input to perform iteration search number 2. No longer the input sequence from here. To perform iteration search for iteration 1, you will use the input sequence, right? Your query sequence, right? And then for iteration 2, 3, 4, and 5, this one discarded, tak pakai lah. What you need is just the newly constructed BSSM for subsequent iteration blast. Okay, dah? Do you understand now?
Yes, doctor. Thank you.
Yeah, it's very simple. And then after iteration 2, you obtain again a good match sequences, and then again multiple sequence alignment will be constructed again, and then converted to BSSM, and then the newly constructed BSSM will be used as input for subsequent search. Macam tu je. And then some until the solution converge. Later I will teach you what I mean by the solution converge. Okay, how many iterations should you run during SciBlast search? Normally, the SciBlast will be conducted for 3 to 5 iterations, normally lah. But it can be less than that or more than that, up to you. Okay, then how are you going to stop? When are you going to stop for each of the iteration blast? What information tell you that you can stop now based on the result that you obtain, right? Until the solution converge. You see, okay, the SciBlast is normally run for 3 to 5 iterations, and then for the SciBlast is converged when there is no new sequence is reported. Okay, for example, these are the table that I constructed using 2 different of the iteration blast. Okay, this one SciBlast A, and then this one SciBlast B. So for SciBlast A against sequence A, and then I calculate sequences with good E value, which is less than 0.05, and then sequences with worst E value, meaning with E value more than 0.005. So I just I calculate the numbers of the hit, and then I fill in this table. Okay, so from first iterations, I obtained 24 sequences with good E value, and then iteration 2, 152, dia akan bertambah, and then third iteration become 208, and then at 4 iterations, it becomes 240, and then sequences with worst E value is 24, and then I continue to iteration 5, and then I noticed that the hit with good E value that reported to me is now saturated, or the same as the same as the iteration 4. So that means the solutions converge. Right? The SciBlast is now converged. Maksudnya sama lah, and then no changes anymore after that. So you should not perform SciBlast further, meaning that you should not perform iteration 6, 7, or 8. You should stop at iteration 5, because the output that reported to you already converged, or same, or saturated. Same as this example. Okay, at iteration 3, the hit that reported to me is 138 with less than 0.05 E value, and then 35 sequences with E value more than 0.005. And then at iteration 4, the same value reported to me, especially this one. If no changes in terms of the numbers of sequences reported to you at 4th iterations, meaning that the SciBlast is now converged, and then you should stop the SciBlast at iteration 4. Understand?
Yes,
Panda. Okay,
Yeah.
it's very easy, right? Okay. Okay, now we try to differentiate between blast and fibroblasts. This is blast, and then this is fibroblasts. And then for proteins have patterns or signature that define them as a members of family. Each of the protein, each of the members of protein in a family, they tend to have the same characteristic, the same signature, or the same factors that differentiate them from others members in others family. For example, lipocalin. Uh, the signature for lipocalin is GXW. And then signature for lipase is the first amino acid, either alanine or glycine, X any amino acid, and then serine, any amino acid, and glycine. Okay, these are the patterns or signature for members of the family for lipocalin and lipase. And then the fibroblasts combine two criteria during the search. The reported hit must have regular expression, meaning that match these patterns, and local alignments. Local alignment, if they can align properly, meaning that they are homologous. Local alignments surrounding the patterns. So if they can report it to you and they can align properly, meaning that two sequences are homologous. So in order for for fibroblasts to report the result to you, it must fulfill two criteria. One is regular expression, meaning that match the pattern that you key in during the fibroblast search, and also local alignment surrounding the mesh. Right? So for the iteration 2 of fibroblasts is indeed the same as fibroblasts. So the difference between fibroblasts and fibroblasts is just the pattern that used to perform the search. And then iteration 2, 3, 4 for the fibroblasts actually is the same as fibroblasts. Summer at the same PSSM will be constructed based on the input sequences from the previous iteration blast, and then if you perform multiple sequence alignment and then convert to PSSM. The blast is a variant of the fibroblasts is a variant of blast, something that is very similar, that focus on the alignment and construction of the PSSM around a motif. So meaning that they fulfill these two criteria. And then the fibroblasts, they perform the search but limit alignments to those that match a pattern in the query. So for fibroblasts, they perform the search. That does not take into account the pattern of the sequences. They just take into account the local alignments of the sequences fibroblasts. And then for fibroblasts, they take into account they don't not only take into account the local alignments, but also the pattern mesh. So two things, right? So we can say that the first iteration for the fibroblasts is using the pattern search, and then the second iteration for the fibroblasts is the same as fibroblasts. Yeah? So how to design a fibroblast pattern? Okay, you have 4 sequences here, right? And then I just show you the conserved motif. I just show you the patterns or signature that differentiate this protein from from other members in others family. So these are the motif for these 4 proteins. Okay, can you design a blast pattern based on these informations? First column, all is alanine, and the second column can be phenylalanine, alanine, cysteine, and aspartic acid. And then the third column again, all histidine, non-variant. And then the fourth column, thyroxine, phenylalanine, thyroxine. And then column number 5, leucine, lysine, asparagine, and glutamic acid. And then subsequently, serine, threonine, valine, isoleucine, alanine, and then lysine, arginine. Okay, based on this information, and you can design the 5 patterns by looking at the grouping information here. Like for example, you see non-polar aliphatic amino acid consists of these members: glycine, alanine, valine, isoleucine, methionine, and leucine. And then for aromatic acid, the acid with ring and the side chain, only these 3: phenylalanine, thyroxine, and tryptophan. And then for negative charge acid or acidic acid, only aspartate and glutamic. And then positive charge acid, lysine, arginine, and histidine. And then the rest of the amino acids are polar acid. You can design the pattern by grouping them according to the information for the classification for each group of the amino acid. Okay, for example, here you see first column is invariant. Okay, so you don't need to put the bracket here because it is invariant. So, okay, for the first column, all of the amino acids are alanine, so it's an invariant. So you no need to give a choice because just put A here,
Doctor,
alanine. Yeah.
Doctor, we can't see your slide.
Okay, forgot to share. Okay, for the first column, all of the amino acids here are alanine, so meaning that it's invariant. Right, so you don't need to provide a choice for them. Just stick down here, alanine. And then for second amino acid, second column, this phenylalanine is a ring amino acid, right? And then alanine is aliphatic amino acid. And then the cysteine is polar amino acid. And then glutamic aspartic acid here is acidic amino acid. So it's from group. So it's very confused. You don't know which of the amino acids should you include into the bracket. Right? If from different group, and then you just provide X, meaning that can be any amino acid. And then for third column, it's invariant, so everything has to be, I forgot, I missed here. So the invariant, so you just list down histidine here. So histidine, and then the column of 4 can be thyroxine and phenylalanine. These two are ring amino acid with the ring side chain. So under the group of ring amino acid, they got 3, right? Either phenylalanine, thyroxine, or tryptophan. So you can provide a choice here in bracket tyrosine, phenylalanine, and tryptophan. And then followed by column number 4. Leucine is aliphatic NSA, and then lysine is a basic NSA, and then asparagine is polar, and then this E here glutamic acid is a acid NSA from different group. Meaning from leucine, from under non-polar aliphatic NSA, and then aspartic acid, and also the glycine, and also the asparagine. So it's different group of amino acid. You don't know which of the group members should you put inside the bracket for as a 5 pattern, and then you just put here X, meaning that can be any NSA. And then the last column is lysine and arginine, only these two. And then you know that the lysine and arginine is example of basic amino acid. And then for basic amino acid, there are 3 amino acids which belongs to basic amino acid. Lysine, arginine, and histidine. And then you can provide a choice here, K, R, H. So we add it together. This is the 5 patterns that you can key in during when you perform the 5 BLAST search. Right? This is how you perform, how you design a 5 BLAST pattern. So take note here, no dash applied to pattern from 5 patterns. Even though the 5 BLAST patterns, the pattern for 5 BLAST, they use the convention from the ProSite. ProSite, they use the dash in between 2 NSA. And then for 5 BLAST pattern, there is no dash. So the difference between the ProSite pattern and 5 BLAST pattern. Okay, after you perform a 5 BLAST search using the pattern and also the input amino acid sequence, and then after performing 5, this is one of the results for first iterations that reported to you. You will see different to BLAST B, you will see something extra here, asterisk on top of the patterns. Okay. This indicates that this region match to the 5 BLAST pattern that you key in when you perform 5 BLAST search. You can only see this pattern marked with asterisk for the sequence alignment for iteration 1 only. Iteration 1 only. Okay? And then as subsequent iteration, just now I told you the difference between 5 BLAST and 5 BLAST search is the 5 BLAST search using additional pattern. And then iteration 2, 3, 4, 5. For 5 BLAST search, it is the same as 5 BLAST search. So for iteration 2, the pairwise sequence elements reported to you in iteration 2, 3, 4, 5 for 5 BLAST, there is no asterisk on top of the patterns. Take note. Okay. And then why BLAST is more sensitive at detecting significantly related aligned residues than PAM and Brosm matrix. Right? Do you know why? Just now I already told you the standard BLAST B use Brosm and PAM scoring matrix. The same PAM and also Brosm for every single BLAST B search, but for BLAST is different. The scoring metric is customized based on the related sequences rather than a group of sequences may not be related. For example, in PAM and Brosm, they use a group of sequences that may not be related to your sequences. Right? That's why it's not that it's not an example of the customized sequence for BLAST B search. Okay, and then we will move to another part, which is HMM, hidden Markov model. Right? Hidden model. to describe the probability of the occurrence of protein sequence. A profile HMM can serve as a representation of a sequence family or sequence domain. Right? The most common application is to compare profile HMM and the sequences in the database. Okay? This type of the HMM sequence comparison are more likely to identify distant homolog than sequence comparison used in most databases. For example, BLAST using sequence comparison. And then here are how HMM is used to score the probability of occurrence of protein sequence. First, multiple sequence alignment of various proteins. Okay, and then we calculate probability of each amino acid aligned in a column. How these amino acids align in the column, and then they convert to probability. Actually, this one is same as a BSSM, right? Okay, and then a score for sequence. You would like to check the profile here, whether which of the sequences match the profile here. You would like to search HARTV, and then from this HNN profile, you can derive a score for HARTV. Right? Okay. And then for this score, you have to multiply the matched individual score if the probability is not listed in launch format. From here, the probability is not in launch format, right? It's just as the normal format. So if you like to provide the score for HRTV, you have to multiply each of the matched probability here, right? If the hidden Markov model that provided to you is in the form of a launch format, you no need to multiply. You just sum up all the individual score if this profile is in the form of launch format. Right? Okay, this is the probability tables is display. This representing the simplified profile HMM. Right? So when we compare HMM with PSSM, it's about the same. If we do not consider insertion and deletion. However, for most of the multiple sequence elements, they are deletions and insertion. Biasanya tak ada multiple sequence elements is without insertion or deletion. Most probably they are insertion and deletion. These are example of the non-gap HMM profile. Ini yang tak ada gap. Okay. This example of non-gap HMM profile for detecting Tata box. Tata box is the promoter region -10. The consensus sequence for Tata box is TAT-AAT. So we can design a scoring metric, a profile HMM, to detect promoter region in the unknown sequences using this score in order to detect is there any promoter sequence inside the unknown sequence. The probability of aligned nucleotide for the promoter region then is calculated from the multiple sequence element for various of the sequences in the database, and then you calculate the probability for the first nucleotide, second, and then third, fourth, fifth, and number 6, and in order to convert into the profile based on the multiple sequence element information. For example, the probability of T aligned at column 1 there are 1, 2, 3, 4, 5, 6, 7, 8 T, and then the total sequence is 10. So 8 divided by 10 equal to 0.8. So the probability for T at column 1 is 0.8. 0.8. And then for probability for G to align at column 1 is 0.4. 2 over 10 is 0.2. Same as the rest. Okay, this is the summarized form of the HMM profile without any gap in between. But however, most of the sequences is a big gap in between. Right? This is another example, big gap in between. Many gaps here. Right? Most of the time, they are insertion and deletion in the multiple sequence alignments. Right? These are examples of the gaps HMM profile. Gaps you see with insertion here. Same thing at column 1, you can do some calculation. At column 1, they are 1, 2, 3, 4 A, 1 T. So the probability for A at column 1 is 4 divided by 5 equal to 0.8. The probability for T aligned at column 1 is 1 divided by 5 equal to 0.2. Right? Very simple, right? And then in between, there is emission probability and also the transition probability. Okay? For the transition probability, yang masuk dan keluar mesti satu. One is the maximum number. To enter into the first column, meaning that the total is 1. And then from column 1 to enter into another column, the total is 1 according to the criteria here. Okay. Now we try to do some calculations. Okay. The transition probability from column 3 insertion table, from column 3 to insertion table here, right, equal to how many yang masuk dalam table? 1, 2, and 3. There are 3 insertion here, right? 3. So 3 divided by 5, total is 1, 2, 3, 4, 5. Yang got insertion is just 3. 3 divided by 5, so it's equal to 0.6. And from insertion here into the next column, which is column 7, is how many? From here to here, 1, and then insertion to here, 2, insertion to here, 3. So 3 over 5 equal to 0.6. You get 0.6 here. Same thing here. From here, from this column number 3 to insertion also, the transition probability is 0.6. So this is how you obtain the transition probability for these two, right? Okay, now you would like to calculate score. You use this profile HMM to score the sequences in database, and then you have 2 sequences in database. Sequence 1 with the sequence TGCT-AGG, and then sequence 2 with the sequence ACAC ATC. These 2 sequences from this one, the first one and the last one, yeah. And the first and number 5th one, number 4th, 1, 2, 3, the first and number 4th. Okay. And then just like I told you, transition probability into the column 1 is the total is 1. Masuk 1, keluar 1. Okay. So at column 1, for the first sequence is T. When you look at here, the T is 0.2, and then the transition probability is 1. 1 direct 0.2 equal to 0.2. And then for the second column is G. G here is 0.2. And then transition yang masuk sini 1.0 times 0.2, you get 0.2. And then the third column is C. C is 0.2. And then transition here is 1 times 0.2, you get 0.2. And then from third column into insertion, right? Into insertion here is T. So T here is 0.2, but the transition here is 0.6. 0.6 times 0.2 equal to 0.12. And then from insertion back to the main state, the transition is 0.6. And then the nucleotide here is A equal to 1. So 0.6 times 1, 0.6 times 1, you got 0.6. Same thing from here to here, the transition is 1. And then the nucleotide is G is 0.2. So 1 times 0.2, you get 0.2. The last one as well, 1 times G 0.2, you get 0.2. Right. Just now I told you, if the priority score here is not in the log or launch format, in order to obtain the final score, you have to multiply, kan? So 0.2 multiply 0.2 multiply 0.2 multiply 0.12 multiply by 6 by 2, and you will get 0.000023. And then if you convert to the percent, it's equal to 0.223 0.0023% for sequence 1. And same thing for sequence 2. The score in percent is 4.71%. So when you compare the score for sequence 1 and sequence 2, which of the sequence is the best match to this profile SMM? Yang mana satu? Which one? Huh?
Sequence 2.
Yeah, the higher the score, the better match, right? So sequence 2 is very simple. Okay, sequence 2. Okay. Okay, we move to the next one. Okay, just now, I asked you the word size for blood N is berapa? The word size for blood N is
11.
11. Okay, the word size for blood P
3.
3.
3. Okay. Okay, the blood N use a short seed with consecutive exact match. Yang short seed here to 11 with exact match. This is plus N, how they perform the search exact match of 11 nucleotide. If this 11 nucleotide, if the first one is the seed or the word they use to perform the search in against the nucleotide DNA database, so if this 11 nucleotide match exactly, maksudnya semua totally match, and then they were expanded in two direction, kan, kanan kiri, kan. Why they were expanded? To calculate what? Dr. Fiza ajar, kan? To calculate what? To extend in both direction to calculate? Huh? So once it's matched, and then they akan extend to kanan kiri to get the score. Okay, the high scoring pair has HP. Dengar HP. High scoring pair. Until their total value to drop to baru dia akan stop to extend in both. So you get scoring pair. This is how BLAST-N is working, right? Okay, another software called as Panther Hunter. This application, they use non-consecutive letters seed, but they still use 11 match 11 match from a total of 18 nucleotides. So this is an example of the seed for Panther Hunter. In total is 18. In this 18, they must match at least 11 in order for the seed to be extended in both directions in order to calculate the high scoring pair. Right? Okay, this is the difference between the BLAST-N and Pattern Hunter. Pattern Hunter use non-consecutive letter as seed, BLAST-N use consecutive seed. Okay. when we compare the length of the seed for BLAST N 10 and also 11, which one do you think that is more sensitive? Actually, the smaller the length, the sensitive the seed. So when you compare the length 10 and 11, you for BLAST N method, the length with 10 nucleotide is more sensitive with as compared to the length with 11 nucleotide as seed. Somehow the Panther Hunter they still they use a longer seed which consists of 18 nucleotide with 11 mesh. It can improve the sensitivity further. This result is summarized in this table. Please take note. I think the note, your note, I think is something wrong with your note. Inside your note here is level expand. This is 11, right? Actually, it's the ballet. The textbook make the mistake. After I read the textbook, and then I found that something is wrong here, and then I go and search the original journal article. I found that something wrong is here. So this is the real one, right? So if the seed is 10, the sensitivity is at the same level of similarity with the number of seed 10, the sensitivity is better, 0.42 as compared to seed numbers 11, the sensitivity is just 0.3. So for the Panther Hunter, use 18 nucleotide with 11 nucleotide of match, they can improve further sensitivity to 0.5. Right? Meaning that the Panther Hunter is more sensitive and also faster because they no need to have exact match in order to extend to calculate the high scoring pair in both directions. Okay. I think you should familiar with this, right? And then this is from chapter 3, the BLAST-P algorithm. Again, how BLAST-P perform the search, they will divide the sequences into three nucleotide. For example, for this nucleotide, in order for the BLAST-P to do the search, they have to derive the seed from here. So the seed from here, it can be L aligned with L, W, and G may totally match, and then you get the score 21. If partially match, you get score I, W, G, you get 19, and then M, W, G, you get 19, L, F, G, you get 11. And then, do you know what is the threshold value for BLAST-P search? The T value for BLAST-P is class. Do you remember the T value for BLAST-P? Dah lupa lah. Huh? Hello? Dr. Pizza dah ada kan? The T value for BLAST-P is 11, right? Hello? If you respond so that I know whether you understand or not, so that I can continue further. Okay, changing the word size for BLAST N is like changing the threshold value for BLAST-P. The smaller word size induce a slower and more accurate search. So if you like to improve sensitivity, accuracy, you have to make the numbers become smaller. The seed number becomes smaller, but it will take longer time to complete the search. With the high threshold value in BLAST-P, some match will miss. So if you use the very high t value here, if a cut off, let's say the default one is 11, more than 11, and then you do the search. If you adjust the t value to 15, so meaning that they exceed the 15, and then they will start to do the search, meaning that the seed, the qualified seed that can perform the search is become lesser, right? Once the seed become lesser, let seed be scored less than the threshold value to be used to calculate the seed, right? And then some of the match will miss. With lower threshold value, more successful extension. So if you set a smaller t value, many of the seed here will qualify, will match, and then they will perform the extension, right? Okay, that's all for this tutorial, and I would like to discuss a bit on the on the practicals, what you should do. Five blast pattern, side blast first, side blast. Okay, these are the practical guide. Later, I will upload to Blast. Okay, how to interpret a side blast result. So the input sequences for your practical is GDSL hydrolysis family proteins, right? And then with this accession number. For some of the protein will be secreted up into the culture medium. And then this type of protein, they have leader sequence or signal peptide. This signal peptide with no function. The function of signal peptide is just to transport the protein from inside the cell to outside the cell. Once the protein is transporting up to the cell, the signal peptide will be cleaved by signal peptides and the brain, and then release the protein into the culture medium. And then the final protein without the signal peptide we call as matured protein. Right? Matured protein. Without signal peptide we call as matured protein. Okay. Protein is normally is extracellular protein. Okay. Okay, you start with this sequence. Before you can perform the alignment to do the search, you try to locate, is there any signal peptide in this sequence? So you how to locate signal peptide from what you learned before, using BLAST P, using a signal P search to locate the signal peptide. And then you notice that this is the signal peptide. And then you have to remove this before you perform the BLAST P side blast search. You remove this, and then you get this. This is the matured protein. Right? Then you can perform side blasters against database. Again, database, I need to set the parameters here. Database PDB. And maximum target, okay, you may increase from 500 to 10,000 if you did not get any of the report. If the output did not divide into those sequences with good e-value, those sequences with worse e-value, and then you have to increase the maximum target to 10,000, right? And then after you perform a search, and then they will report to you those sequences with e-value less than 0.05, and then those sequences with e-value worse than 0.05, and then you consider how many proteins, how many hits here, and then you summarize in the form of the table. You must include it into your practical report. Right? Summarize this, and then this is very important because and then you get to know at what iteration, at what point the BLAST search is converged, and then from here we know that at iteration 3 the BLAST search is converged because the numbers of protein reported to you with significant e-value remain the same at iteration 2 and iteration 3, right? So okay, and then this is the first part, and then the second part is you have to change the database to red-set protein. See the red-set protein, there are many of the sequences in the red-set database. So you have to limit the search to a particular organism. Okay, here you may limit the search to photobacteria only. If there are too many sequences reported to you, the output may not be divided into two sections. This is e-value less than 0.05 and e-value more than 0.05. So if you set the limit to particular organism, the numbers of hits reported to you will be smaller, and then they will report to you into two sections. This is for BLAST, and then for another part of the experiment, which is BLAST. And then same thing. First, you have to locate the synapeptide and remove the synapeptide. Okay, and then perform. Before you can perform a BLAST search using the 5 pattern that I provided to you. Right? And you perform the search using the 5 pattern I provided to you. Okay, and then you get the output. So, and then I also ask you to design your own 5 patterns, right? So you can design anywhere from the aligned multiple sequence alignments to design your own 5 patterns. It can be very close. It can be from anywhere. You can do the literature search to search which one is the motif. Okay, for example, for GDSL esterase, we know that the motif is at the N terminal surrounding the serine, the residue, which is the catalytic trias. Right? I forgot to provide the multiple sequence alignments. Okay, after you obtain a multiple sequence alignment at one particular region, which is motif here, knowledge is surrounding the GDSL here, and then you can design a pattern based on this region. Okay, for example, at this region, T, it may align with different amino acids, and then T is one of the amino acids under polar amino acids. Right, so you can provide the choice of every single amino acid in the bracket. So for the 5 BLAST to select. So from here, T can be the choice for T can be this amino acid. And second one, also the same group can be the same amino acid. And then for the third group, it's the ring amino acid. So the ring amino acids with the ring side chain only 3: phenylalanine, tyrosine, and tryptophan. And then GDSL here is conserved, so you cannot change any. That's why you have to remain invariant GDSL. And then the rest, serine here, serine is example of the amino acid with hydroxyl OH group. So for OH group amino acid, it can be serine or threonine, or it can be any of the amino acid in this group. It's up to you. There are many ways to design the pattern. You can provide this, or in bracket just consists of serine and threonine. And then the second last here is as acidic acid, only two is either aspartic or glutamic acid. So the choice is D and E. And then the last one is aliphatic non-polar amino acids. So these are the choice of acid in non-polar aliphatic amino acid here. Okay, and then you use this sequence to perform the 5 BLAST search, and then this is the output that reported to you with asterisk on the top, and you have to capture this the whole sequence into your report for you to discuss, right? And then at subsequent iterations, iteration 2 and 3, you will see there is no asterisk on top. No asterisk on top, right? For the pairwise sequence element as iteration 2, 3, and 4. This is because at iteration 2, 3, and 4, for the 5 BLAST is actually the same as Psi BLAST. It's actually is a Psi BLAST search as iteration 3 and 4. Right? This basically what you have to include it into your report. Okay? So is there any question for today's discussion?
No, doctor.
And then, okay. And then I will post the question to the forum for discussion. I think by this week, and also upload the video for you to watch the video, and also the answer the forum, right? So that you know better this chapter. So and then, so I have covered all the advanced database searching, and then for the next chapter will be multiple sequence elements. The same things. Week 8, I will provide you the video for multiple sequence elements, and then week 9, I will do the same thing, the same discussion here to explain in detail what should you know in that chapter during week 8, week 9, and then week 10 is the second test, right? The second test, online test, maybe it's just a simple test lah. Okay? If you would like to have a more tutorial before the test, you can let me know. I can arrange. It's okay for me. Anytime.
Okay,
Okay?
doctor. Okay.
Yeah, doctor.
Okay. Thanks for joining today's discussion. Okay, see you.
Okay.
Thank you,
Thank you,
doctor.
Thank you, doctor.
If you don't
Thank you,
understand,
doctor.
if you don't understand, you can always text me, email me, or post the question in